Okay, this is it, the last video of the semester. So this last video is on Hofmann elimination, and this is a way to make an alkene from an amine. So just like alcohols, amines can serve as precursors for the synthesis of alkenes. Okay, so in Hofmann elimination, the first thing we do is react our amine with excess methyl iodide. And so we know that this is going to give us exhaustive alkylation, and that's going to give us our quaternary ammonium ion, and then it'll combine with iodide as the counter ion to give us a quaternary ammonium salt. And what I've done is I've converted something that is a bad leaving group, NH2, into something that is an excellent leaving group, this trialkylamine. So now that I have a good leaving group, I can use a strong base to get E2 elimination. In this case, the base that is most commonly used is silver oxide. When we use silver oxide, we actually replace the iodide counter ion with a hydroxide counter ion, and hydroxide then causes elimination. Part of the reason silver 1 oxide is used is the silver will precipitate out with the iodide, because we know silver halides are insoluble. And so in a two-step process, we first use excess methyl iodide, then use silver 1 oxide as the base, and that will give us the elimination product. All right, so this overall reaction of converting the amine into the alkene is called Hofmann elimination. And you may have picked up on an important aspect of this Hofmann elimination, and that is the regiochemistry. Normally, when we have E2 reactions, we're going to get the more substituted alkene. In this case, we get the less substituted, less stable alkene. Now, when we first learned about elimination reactions, we talked about one name that we would give to the more substituted product is the Zaitsev product, and the less substituted product is the Hofmann product. Same Hofmann. Now, to see why we get the less substituted alkene, we need to remember something that we learned last semester when we first learned about E2 reactions, and that is that the leaving group and the hydrogen that's being eliminated have to be anti-periplanar from one another. And so, to remind us of what that means, let's go to the next slide. So this has to do when we were talking about conformational analyses of alkanes, and when we would draw these Newman projections. And so if I try to get the more substituted alkene, that transition state where the leaving group and the hydrogen that's being eliminated, the requirement that they have to be anti-periplanar to one another, means that I'm going to get a Gauss interaction, an unfavorable steric interaction between this big alkyl group and this big, really bulky leaving group that I've made. And so that makes, because this transition state is going to be high in energy due to this unfavorable interaction, this makes it hard to make the more substituted alkene. When we go to make the less substituted alkene, you can see that we don't get this Gauss interaction between this bulky alkyl group and this really big, bulky leaving group that I've created. And so this is why the less substituted alkene is generally preferred in these Hofmann eliminations. So when we talked about getting the less substituted alkene previously, when we were doing eliminations of alkyl halides, it was the base that was bulky that gave us the less substituted alkene. In this case, it's the leaving group that's really bulky and is driving the production of the less substituted alkene. Or another way to visualize this is using reaction energy diagrams. So the more substituted alkene is in fact lower in energy than the less substituted alkene, as of course we would expect, but because of that Gauss interaction, it gives a really high transition state energy to make the more substituted alkene. The barrier for forming the less substituted alkene is much lower, and so this is generally the preferred product in these Hofmann eliminations. Okay, so one final example. So I want to predict the major product when this amine is reacted with excess methyl iodide and silver 1 oxide. So this is going to give me a Hofmann elimination. And then the trick is predicting the major product. So I've got 3 groups coming off this carbon that's being eliminated. I can't put the double bond here because this benzene has no hydrogens to be eliminated. So the double bond's either going to go here on the methyl group or here on the ethyl group. Now, we just talked about the regiochemistry of this Hofmann elimination is going to give me the less substituted alkene. So my major product in this case will be that alkene.